All right, so this should be about where we left off. The net torque we figured out was equal to R times mu times N times G. And of course, net torque is also always equal to I times alpha. And we figured out the net torque was clockwise. And so the angular acceleration is always in the same direction as the net torque, just like the regular acceleration is in the same direction as the net force. So our angular acceleration had to be clockwise. And since net torque is always equal to I times alpha, the angular acceleration, is equal to the net torque over I, the moment of inertia. So we'll just take this thing we found right here. We figured out that the net torque was R mu mg. We need to divide that by I. Of course, we are dealing with a ring because it's a hula hoop, and so the best thing we can approximate it as is just a thin ring, which has a moment of inertia of mr squared. But of course, different objects, you'd have to use different moments of inertia. So we plug those in. You can see our m's are going to cancel as well as one r, which means that our angular acceleration clockwise is going to be mu times g over r, so the coefficient of friction times g divided by the radius. Remember that was clockwise though, so when we write this as a vector so that we can actually plug it into our kinematic equations, I don't know why I have an m in there. The angular acceleration needs to be negative mu g over r, because it needs to be clockwise. And so that negative sign is how we make sure that we communicate the clockwise information into our kinematics. So from there, we're going to take the acceleration, which we figured out as a vector, including sign convention, negative mu g. The angular acceleration, negative mu g over r. These equations are only so similar to each other because we're dealing with the hoop and the moment of inertia just sort of like works out like that. Any other object, they're not just going to be off by an r. So make sure you're always actually solving the problem for the object you're dealing with. And then we're going to take both of those and plug them into this equation that we built. So that should look like this. So we have our combined kinematic equation, and we're just going to plug in the two things that we found, which should give us this. Over in here, just a couple things. So we're plugging a negative value in for alpha. So the minus sign combines with that minus sign to become positive. We'll also have an r from this term and divided by r from this term, so we're going to have our r's cancel out over here. And so that'll sort of simplify down to, initial velocity minus mu gt equals negative r times initial angular velocity plus mu gt. And so we need to solve for time. So we're going to combine our like terms. So we've got a plus mu gt on this side. We've got a minus mu gt on the other side. We're going to get those both onto the right side. So we'll add mu gt to each side and get, down on the next line, you can see we have 2 mu gt. And then we got to bring this term over to the left side, so we'll add r times the initial angular velocity to the left side. We get initial velocity plus r times the initial angular velocity is 2 mu gt. And then since we want time, just solve for t. Divide both sides by 2 mu g. When you're plugging your numbers in, remember we are dealing with vectors, and so the signs are important. You don't actually have to have written the little +2 and the +3, but just remember, like, the whole reason we went through all of this work to make sure our signs were still included was because when we do the kinematics, we got to make sure that we plug in the right signs for our values. So your initial velocity is +2 because it's moving to the right, so that's going to be +2. The initial angular velocity was +3. Everything else, I would just plug in our information, and when we divide it out, we get 2.4 seconds. Since we did a whole lot of work and a whole lot of combinations and stuff to get this, it would be sort of nice if this was, like the AP test and you just wanted to quickly check and see, is this equation reasonable? Is there a good shot that this actually worked? And we've talked about the easiest way to check that is with units. That'll at least tell you if your answer is reasonable. It won't tell you for sure if everything's right, like if you got the wrong constant on the bottom, it's not gonna tell you, but like a lot of math mistakes will cause a unit error. And so we can check our units. So we want to know, does this actually work? Does this equation on the left actually generate a time? And so velocity is in meters per second, radius is in meters, angular velocity is in radians per second. 2 and mu both don't have units. Remember, coefficients of friction are just ratios, so only g has a unit, meters per second squared. Remember, radians are special because they're just a ratio. They don't work like normal units, and so we really only write radians when they're by themselves. So when we got radians in the numerator, so it's not just 1/seconds, we got radians per second. When we combine them with anything else, the radians basically go away. They sort of become invisible. So when we do meters times radians per second, we just have meters per second. So meters per second plus meters per second over meters per second squared. Top is going to be meters per second. Bottom is meters per second squared. To divide fractions, multiply by the reciprocal. And we can see our meters are going to cancel out. All but one of our seconds is going to cancel out, which is exactly what we want. If we were supposed to get time, our unit needs to be in seconds.